Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to lesson 11-1. We're going to start taking a look at quadratic and square root inequalities. Now it sounds daunting, but it's actually not that bad. We're going to take it back just a little bit. Do you remember in another unit how we started off talking about dog kennels, playing with quadratics a little bit? It's been a little while. We're going to come back to that for just a moment. We're going to start off with question number 1 on student activity sheet number 1. Just a little bit of review, just kind of bring it back. So the deal is that Jill wants to create, and I'm going to bust out my pen. I have a feeling I'm about to need it. Jill wants to create a rectangular garden. And Jill wants that garden to be 150 square meters in area. Now, she wants the length to be 5 meters greater than the width. So here's what we're going to do. I think I know where my mouse is. Yep, there it is. So if my width is x, then that means we want my length to be 5 meters more. So that would be x plus 5. And of course, length times width would give me 150. Boom. Yay. So what should the dimensions be? What should her length and width be? All that good stuff. So I think I already helped with the first part, writing an algebraic equation that represents Jill's problem. And then I want you to show the solution to the problem, both graphically and algebraically. So you may need to multiply through a little bit and solve it, as well as use it to help you graph it. Yes, you can totally use Desmos to help you graph it. I will not argue with you on that one little bit. Remember when we graph it, how we graph y equals on the left side and y equals on the right side? Yep, it'll work just fine. So go ahead and hit pause to work this out and then hit play when you're ready to check your work. So I'll tell you what. Oh, I have so many things here. Hang on, I'm going to put that away. I'm going to pull this back out. There we go. Great. So did you graph it? It probably was the easiest way to start off with, wasn't it? So if you would have graphed this and worked your way through, you could have found your answers. Again, you also could have just solved it. So if you multiply, if you distribute, you get what? X squared plus 5x equals 150. And of course, we know with quadratics, we like it to equal 0. So I'm going to subtract 150 from both sides. So I get x squared plus 5x. And I'm now going to say it's minus 150 equals 0. This does factor. What times what would give you negative 150? That would add up to 5. I believe if you do x minus 15, I'll put my parentheses around that, times x plus 10. Hey, that should work out pretty darn good. Negative 15 times 10 is, of course, negative 150. And if you add them, oh, I got them mixed up. That should be plus. And that, hang on, where's my eraser? Let me erase that. And that should be minus. See, even I mess up sometimes. Good times. All right, so if I multiply those, I get a negative. If I add those, I get a positive 5. Yay, great. Which means if either of these were to equal 0, then I would either have to have x equals a negative 15 or x equals 10. Now, you guys are not dumb. You guys know what the deal is. I'm going to get a slightly different color going on here. You know, of course, that if x is my width, then that's definitely not going to be negative. That's weird. That doesn't work. But I will happily take a width of 10. And of course, if x is 10, that means if my width is 10, that means my length must be 15. Here, let's see. And I also graphed it. I graphed the left side, graphed the right side. So here it is. This is a little bit prettier. So here's all our work. We said the width, it can't be negative. So that means my width must be 10 meters, which means my length must be 15 meters. And if you had graphed the left side, y equals x times x plus 5, and then graph the right side, y equals 150, you would have seen that it hit in 2 places. It hit at negative 15 and it hit at 10. And we said, you're no good, buddy, because you're negative. So we stuck with this guy up over here. Let's go to question number 2 on your student activity sheet. Coming back to the dog kennel problem, and again, it's been a while. I will grant you, it has definitely been a while. So coming back to that dog kennel program, remember the deal? Martha and Tyrone, they started their own little dog kennel business, and they wanted the dog kennels to have a perimeter of 30 meters because that was the fencing that they could get, seemed to work out best. And we wanted them to have an area of at least 50 meters. And remember how we made a table and we tried like all these different kinds of stuff. And when we worked it out, we figured out, well, a 10 by 5 would have a perimeter of 30, and it would also give me an area of exactly 50 meters. But if you recall, a 10 by 5 was not the only kennel that would give us an area of at least 50 meters. We said we were cool if it was a little bit more than that. So what I would like you to do is I'd like you to finish off your table. The first part of this is all done for you on question number 2 on your student activity sheet, but I would like you to keep going. Notice how we kept decreasing the length and increasing the width so that we could keep the perimeter at 30, and that kept changing our area. So if you keep going and finish off this table, we can keep this party going. Let's go ahead and hit pause to work that out and hit play when you're ready to check your work. All right, people, how's your table going? Let's hit the button and see what happens. So our next perimeter that we did 10 by 5. And so from there, we did a 9 by 6. That would give me a perimeter of 30, and it actually gives me an area of 54. If we keep this going, that means my next one, I'd have a length of 8 and a width of 7. So that way I still have a perimeter of 30 if I add them all up, but 8 times 7 will give me an area of 56. The last little guy down there just has an X for your width. Hopefully you're noticing a pattern here that whatever my width is, my length and my width have to add up to 15. You remember that? So if my width is X, then my length should be 15 minus X. And if I multiply them together, of course, that would give me my area. Now, originally, we did this as an equation, right? We set that equal to 50, and then we solved it, and we did all that good stuff. But you're noticing now that this is actually a different situation. Remember, they actually want areas of at least 50 square meters, okay? Which means it doesn't have to be 50. An area of 54 is fine, an area of 56 is fine. So we actually have a couple of different kennels that would fall into that category. Question number 4, can you think of another kennel that might meet those requirements? Sorry, that's not question 4, I apologize. Question number 3, can you think of another kennel that might also meet those requirements? And just jot it down. Once you've got that, I'd like you to consider question 4 and question 5 as well. So go ahead and hit pause, work your way through these, and then hit play when you're ready to check your work. So I don't know about you guys, but I was realizing there are numbers in between these that would work as well. Like I could have a perimeter, or pardon me, I could have a kennel with a length of 9.5 and a width of 5.5. If I added those together, I would definitely be at 30. And if I multiplied them, I would be over 50. And that's just one example. There's tons of them. In fact, there's so many. Once you start thinking in terms of decimals and fractions, there's so many. I don't think there's only a set number of answers. I think there's a lot of them. So if we come over here, this is what we call question number 4 was saying, hey, can we write, we don't want it to be equal to 50 meters exactly. Can we modify our equation a little bit to represent kennels with areas of at least 50? So I'm cool if it's equal to 50. I'm cool if it's more than 50. So remember your inequalities. Yeah, you remember these bad boys? Less than, greater than, less than or equal to, greater than or equal to. So I'm okay if this is greater than 50. I'm okay if this is equal to 50. I just don't want it to be less than 50. It's the only thing I don't want. So there's a lot of inequalities. There's a lot of possibilities. There's a lot of things that together could give me more than 50. So that's interesting. There's a lot of solutions then. Question number 5 brought back to the pendulum problem a little bit. Remember this little guy, our pendulum problem from earlier? And remember how we had a problem where we said equal to 0.8 exactly? We're like, I need that to be exactly 0.8 for my clock to do what we wanted to do. And we used a table and we're like, it should be between 10 and 20, right? 0.6 to 0.9, 0.8's in there. I think we got like 15.9 centimeters long, something along those lines. Now, let's say the clock has been fixed. It's keeping perfect time with its little 0.8 second period. Yay. But you feel like annoying your parents and you want to make the clock run a little bit faster. Why are there so few hours in the day? So to do this, you'd like to know what pendulum lengths would ensure that the pendulum takes fewer than 0.8 seconds to complete one cycle. I wanted to go faster than that. So this leads to another inequality. Instead of saying this junk here equals 0.8, I'm going to write that this stuff here is less than 0.8. So just like with the dog kennels, this means there's a lot of solutions here. There's a lot of solutions here. So the question is, how do we find them all? And that's the big question for this unit, guys. Now that we can see with these inequalities, there's so many solutions. There's an infinite number of solutions. The question is, how do we find them? So we're going to use some of our techniques that you've used before. We've made tables before, which means you might want to have Desmos handy. We have made graphs before, tables. We've used Desmos to help us do both of those things. So we're going to use some of those same techniques to help us solve our inequalities. We've used them in the past to say, oh, look, it's equal, and that helps us find our solutions when they're equal to each other. But these tables and graphs can actually also help us solve inequalities. And of course, our algebraic methods. We did a little bit of algebra at the very, very start, but we're going to see as we move through this unit how algebra can help us solve these little guys as well. So if you come over to student activity sheet number 2 to question number 1, here's our dog kennel situation, right? Our lovely dog kennel situation where x times 50 minus x is greater than or equal to 50. So remember our intersection points that we did earlier? We did do those earlier. And we found it by graphing the left side and we graphed the right side and we're like, where do they intersect? There's the magic. We also had a table that we made. Here's what I kind of want you to think about. Compare the kennels represented by the 2 sets of intersection points. So we said we had 2 solutions. We had one here, one here. Can you just for a moment make a little note down there underneath question number 1, about these 2 kennels when x equals 5 and when x equals 50. Go ahead and hit pause to give that some thought and make some notes, and then hit play when you're ready to continue the discussion. Hopefully you noticed they're actually kind of the same rectangle. They both give an area of 50. The one is a 5 by 10 rectangle and the other is a 10 by 5 rectangle. So they're actually the same rectangle, just one got flipped over onto its side. So you actually have the same rectangle, whether you plug in a 5 or whether you plug in a 10. A rectangle with a width of 5 gives me a length of 10 and an area of 50. But a rectangle with a width of 10 gives me a length of 5 and thus gives me the exact same rectangle. Yeah. Now, of course, this was just when they were straight up equal to each other, but we were saying we're not concerned about when they're equal to each other. We want to know how to solve this darn little inequality. And in this case, our inequality is saying that x times 50 minus x is greater than or equal to 50. So if you flip over to question number 2, 2 and 3, we got some stuff going on. And here's what we're going to do. I'm going to show you. You actually have the graphs right there on your lovely paper. Actually, before I show you, you have the graphs on your paper on question number 2. I want you to look at these 3 different points and interpret each point in context of the problem, this whole dog kennel versus the area of a dog kennel kind of a thing. I would like you to answer each of those questions, what's going on with each of those guys on number 2. And then on number 3, I want to see if you can make a generalization about the values on your graph and what this tells you. When you analyze the points above, what does it tell you about the solutions to your inequality? Go ahead and hit pause to make some notes on question 2 and 3, and then hit play when you're ready to check your work. All right, so the first point they gave you was x equals 2, so I'm going to move it up here to x equals 2. Now, when x equals 2, it looks like the area of my rectangle is sitting at about 26. 26 is not greater than or equal to 50. So 2 is totally not a solution, right? Because my area is not big enough. The next one they gave you is x equals 6. So I'm going to move over here a little bit, and I'm going to go to x equals 6. Ooh, when x is 6, it looks like I get an area of 54 in my kennel. And that is definitely greater than 50, right? That was the whole goal here, greater than 50, yay. That's totally greater than 50, which means that 6 is most definitely a solution. And then if I keep going to the next little guy, you have 12, right? When x equals 12. So when x equals 12, oh, I only have an area of 36. That's not sufficient, right? We wanted our area to be greater than or equal to 50. So 2 and 12 are not solutions, and 6 was a solution. So looking at question 3, what kind of a generalization can you make here using these points? Well, guys, it looks like my solutions are whatever is going to be above my 50, which makes sense. It said, when is my parabola going to be greater than or equal to 50? There it is, right there. So I need to be looking at values of x where my parabola is going to be above 50. I think this takes us to question number 4. Oh, it does. So how would you describe the solution? So we've said, okay, I'm looking for any value of x where my parabola is going to be above 50. So now that you made a note of that on 3, on number 4, let's see if we can get a little more specific, okay? Let's see if we can get a little more specific and see if we can actually get some mathy kind of algebra-y stuff in here. So I'm going to play this. So as we were saying, below, and when we get to 5, it finally equals 50. But this means that any value of x that's less than 5 is also going to give me an area less than 50. It's not going to be a solution, is it? But then we were just saying that any value between 5 and 10, any value above, any part of my parabola that's above 50 works. So anything that's greater than or equal to 5 and less than or equal to 10, yeah, is good. 5 and 10 are good, and anything in between 5 and 10 are good because those all give us areas greater than or equal to 50. But once we move past 10, the area starts dropping down again, which means that when I have values of x that are greater than 10, that's when my parabola drops down below y equals 50, and suddenly those are not solutions anymore. So we said less than 5 was bad, greater than 10 is bad, in between is good. So I think this answers question number 4. This means that our solutions are 5 is less than or equal to x is less than or equal to 10. So 5 to 10 are my solutions. If you want, I know we've become really keen on interval notation. You could have also written it as 5 to 10 in interval notation using closed brackets because 5 and 10, equal to, right? It's equal to. So I use little closed brackets on that. So this is interesting. I was looking at where my parabola was above 50, but I was following along on the x-axis to find my solutions. So while this little chunk of my parabola is above 50, my solution, that tells me my solution is from 5 to 10. That any value of x between 5 and 10 should give me an area on that kennel that's going to be greater than or equal to 50. Which means, yeah, there's an infinite number of solutions. I can pick 5, I can pick 10, I can pick 7, I can pick 6.293. You get the picture. There's a lot of solutions. So I really like the graph. Don't get me wrong. The table is great. And you can see on the table, I have several different solutions. The only issue with a table is, well, tables are great just for that initial investigation. And when we started this problem, the table was awesome, right? We can see, oh, I've gone above 50. Oh, there's a couple of them over there. The issue with that table, though, is, of course, it can't show you every single possible solution. So the table is great to kind of help you get started and help you see the patterns and the trends and what's going on. But the graph was definitely easier and a little bit better for finding all of my possible solutions. All right, guys, as always, I hope you found this helpful and I hope you found this useful. If you've got questions or concerns, please feel free to email me or come see me after school Tuesdays and Thursdays. You know I'll be around and I'll see you soon. Bye.